This conference will now be recorded.
Hello everyone. So we are starting a new chapter, S block elements. So before starting S block elements, if you think about the periodic table, so here in the right hand side you can see very simple picture of periodic table we have here, right? Now in this periodic table, in the left hand side part, that is actually zoomed, and in that part there is actually S block present. So it is basically in the left hand side of the periodic table. Now this part is D block, and here we have P block. So after finishing S block, there is the next chapter is P block, and this block, which is completely, that is it is lying down in the periodic table horizontally, that is known as A block. So here we will focus on this part. Now when we are talking about S block, there are basically two groups, group number 1 and group number 2. Now the reason behind why there are only two groups, the reason is, if you think about S orbital. Now in S orbital, maximum capacity of electrons is 2 electrons. So we cannot place more than that, whether it is 1s, 2s, 3s, whatever. Now that is the reason when we have one electron, that is ns1 configuration. Suppose I am writing ns1. N may be any period number. It may be 2s1, it may be 3s1, it may be 4s1, whatever it is. If it is ns1 general electronic configuration, then you will have group number 1. And then you add one more electron. Now there are total 2 electrons. So now maximum capacity is reached. When maximum capacity is reached, it is ns2, and now we are getting group number 2. So this is the it is the reason why we have only two groups, because maximum capacity of electrons in S block, it is 2. So this is the reason why two groups, why not more than that, and why it is S block. And the reason is the last electron of the element which we are considering in S block, in all these elements in this particular block, the last electron enters the outermost S orbital. So that is the reason, depending on the last electron, whether it is entering S orbital or it is entering P orbital, we can have different blocks. So as it is entering the outermost S orbital, so that is the reason we are including them in S block. Fine. And there are total two groups. So two groups under S block of the periodic table, as maximum capacity of S orbital is 2 electrons. This is the reason. So here, this group number 1, the elements belonging to these two groups, commonly we call them as alkali metals. So here you can see the first group, it is mentioned here as alkali metals. Now why we are calling them in such a way? Because the oxide compounds of these elements under group 1 and they are hydroxide, they are alkaline in nature. What is oxide? What is hydroxide? Hydroxide means HO minus group, that is ion, that will be present in the compound of these elements, and oxide means it is forming compounds with the element oxygen. Those compounds are oxide. So detailed discussion will be we will cover separately, but here we are trying to understand the reason why these elements under group 1, why we call them alkali metals. The reason is they are oxide compounds, they are hydroxide compounds, they are alkaline in nature. And the group 2, we call them alkaline earth metals. So in the previous name, it is alkali metals. And here the name is alkaline and also earth metals. That means it is their oxides and hydroxides. They are also having some alkaline nature, just like group 1. But another reason why this earth term is mentioned here, the reason is their oxides are obtained in the earth crust. So that is the reason group 2 elements, we call it as alkaline earth metals. Fine. So this unit, that is S block elements, as the name suggests, from the name of this unit you can understand, here it is all about their properties, that is chemical property, physical property, their uses, some important compounds, that is commercially important compounds that are made from these elements included in group 1 and group 2, and also biological importance. Now here under group 1, first we will finish group 1, and once we are done with group 1, then we will start group 2. So in group 1, here in this column you can see what are the elements present. Let's have a look. So here we have lithium, the first element, and here we represent it as Li. Here in the left hand side upper corner, the atomic number is given. Fine. And in the right hand side, the mass is also mentioned. So these are the atomic numbers: 3, 11 for sodium, then we have 19, which is for potassium, then we have 37, which is for rubidium, in short it is Rb, then cesium, and the last one is francium. Though mostly the discussions, that is their uses, properties, it will be restricted up to this, because francium is radioactive, so we will not talk about much that is related to any information related to francium that is not easily obtained, so we will not talk about much francium. Fine. So here 3, 11, 19, 37, 55. Fine. So it is easy to remember, because when you move to 3 to 11, that is you are moving from, this is second period, right? This is third period, fourth period, fifth period, sixth period, seventh period. So in second period, it is 3. So when you move from 2 to 3, if you simply add 8 to 3, you will get the next atomic number. That is the next element's atomic number. Then 11 to 19, this is also 8. Then 19 to 37. Now it is different. You will see it is 18. If you add 18, that is with 19, if you add 18, you will find this. And then we have 52. So how we will find it? It will be, you have to add 32. So whenever you are moving to the next period element, 8, 8, 18, 32, these numbers, if you simply add, then you can find the atomic number. So it is not just blindly you have to remember all this, just lithium first, which is 3, then add 8 to get the next element's atomic number, then again add 8, then 18 to get Rb, that is rubidium, from 19, and finally it is 55, that means 32. So these numbers, it is not that something arbitrary. 8, 8, 18, how we are getting it? Because 8 is Ns2Np6. So total number of electrons 2 plus 6. Same is all same explanation also for 8. But when it is 18, that means except 8, 10 more electrons, and that is coming from d orbital. And when it is 32, that means some more electrons are there, 14 electrons more. So where from it is coming? It is because of F electron, that is maximum capacity is 14. So these are the reasons when we move from one period to another period. These numbers, if you add, you will get the atomic number. So it is another way so that you can remember the atomic number, because sometimes there will be some question which to answer those questions you will need to remember all these atomic numbers. Fine. So after introduction of S block elements, now we will start group 1 elements. So group 1 elements, another name is alkali metals, right? So here we have in this block only the alkali metals with their symbol. Total 6. So all of them are metals, which is clear from the name, because we are calling them alkali metals. They are very soft type of metals. It is not that all the metals in the periodic table they are soft. No, it is not that. You will find some metals from D block that are not soft. But these metals which you are getting from S block, it is a special unique behavior of them that they are soft. Why they are soft? We will also go to that point. But it is a characteristic. They are soft and they are very, very reactive. Remember, whenever you have any elements in the left extreme of the periodic table or in the right hand side extreme of the periodic table, mostly you will find they are reactive. Obviously, except that is, I'm not talking about noble gases, which is also at the right hand side extreme of periodic table. I'm not talking about that because they are stable. Every element they are trying to achieve the noble gas configuration, because they all the elements they are trying to become stable, and trying to become stable means they are trying to achieve noble gas electron configuration. So though that is at the right hand side extreme of periodic table, but I am not talking about that. In the right hand side extreme, if it is 18, there is also group 17, there is also group 16. So I'm talking about those groups where non-metals are present, that is halogens, oxygen, sulfur. So these elements are also very reactive. So when you have in the left hand side extreme or right hand side extreme of the periodic table, except noble gases, then you will see they are actually very reactive. Oxides and hydroxides of this element are basic in nature. So we have already discussed this reason, and that is why we call them alkali metals. And because of their reactive nature, obviously you cannot expect them in nature in free state. So what I'm trying to say is that lithium, sodium, potassium, rubidium, if you consider their natural, how they naturally exist, obviously they do not exist in the elemental form. You will always find them in the compound form, because they will always try to react with some other element. They are themselves very reactive. Okay, so that is why they are not found in the nature in the free state. They are found in compound form. Rubidium and cesium, that is these two, they are found, that is we obtain them in a very low quantity. Okay, and their minerals are basically mixed with other alkali metals. And francium, this is basically radioactive, and obviously you cannot expect appreciably in nature. And how that is radioactivity, if you want to know the intensity, how much radioactivity is, then see its longest lived isotope, which is 223 francium. It has half-life of only 21 minutes. That means it is very low value. So if it is some days, suppose I am saying 20 days or 30 days, that means it is comparatively stable, but it is 20 minutes only. So it is very reactive. So our discussion related to group 1 elements in this chapter, it will be mostly up to cesium, not including francium, because of its radioactive nature. So here you can see, here you can see their abundance in earth crust. So if I'm saying simply abundance, that is not enough information, that is incomplete information, because abundance may be in different form. So here it is in the column, it is clearly mentioned, it is in earth crust. What is the percentage? Not in any, that is not in air or any other part. It is earth crust. So in earth crust, lithium, this is the percentage. Mineral source, the name is spodumene. So you can get question like the source of mineral, the source of lithium, which mineral? So there may be 4 options. With one of these option you can find this, and that will be the correct option. So see, this is a formula, LiAlSiO3 whole 2. So aluminum is also there, silicon is also there, oxygen is also there, but lithium is present. So this is the source. Then sodium 2.27, rock salt. Now you all know this. Then potassium 1.84, its mineral is sylvite, which is the main component is potassium chloride. Then rubidium and cesium, this is very, very low compared to the these two, 0.0078, 0.00026. So this is even lower. So there is no convenient source for these two elements, but we can obtain it, mostly obtain it in the byproduct of lithium processing. So when we process lithium, that is metal extraction from different minerals, so when we do it for lithium, then we can get rubidium and cesium. So there is no direct source, which you can see for these 3 cases, but for these 2 there is no convenient source. Okay, electronic configuration of alkali metals. So as we have already in the first slide, we have seen that maximum capacity of S, it is 1 electron, and then you place another electron, then capacity is reached. But when it is group 1, it will be only 1 electron in S. That means configuration, general configuration should be NS1, isn't it? Now this N may be depending on which period the element belongs to. Depending on that, this N value may vary from 2 to 7. So here in this table you can see symbols are given along with the atomic number. Now how to write the electronic configuration? So suppose just take the first one. It is very simple. It is lithium. So when it is 3, that means it is 1s2, then 2s1. So 3 electrons reach. That means electronic configuration is done. But see, as you will move down, gradually the atomic number will increase. That means number of electrons are also increased. So this is very simple. But just when you will move to cesium or francium, this will be very long, the electronic configuration. See, it will be like this. So for lithium, with atomic number 3, it is 1s2, 2s1. Then for sodium, it is even longer. That is, now you have to write more. It is 11. So total 2, 2, and then 6 plus 1, that is 7. So it is 11. Then for potassium, rubidium, cesium, and now see for francium it is not even written, it is so long. So better you write this electronic configuration in this way, which is simpler way to represent. So in this case what we have done, just for lithium the previous noble gas is helium. Previous noble gas means the last noble gas. So noble gases are helium, neon, argon, krypton. Now helium, it has atomic number 2 and lithium is having 3. That means the previous there is a last noble gas with respect to lithium, it is obviously helium. So instead of writing 1s2, you can write helium and then write 2s1. Now for lithium, you may think that why it is required, but see, as you will move down, it will be very complex. So rather than writing this whole, better you write with the last noble gas. Fine. So for potassium, the last noble gas is atomic number is 18, which is argon. So argon we have written within third bracket and then NS1. In this case, N value is 4 because it is fourth period. Then for rubidium, the last noble gas is 36, that is krypton, and 5s1, that means it is NS1. So general configuration will be noble gas, that is the last noble gas with respect to that particular element within third bracket, and then you have to write NS1. So for cesium it is xenon because xenon is having atomic number 54, just one more electron, and for francium it is radon. So see, when you write the electronic configuration this way, it looks like this. So the conclusions that we can draw, the general valence shell electronic configuration, you have to represent it like this rather than writing this total lengthy electronic configuration. No, that is not required. You can present it simply like this. N is the period number. So for lithium, see, it is second period, so 2, third period, fourth period, fifth, sixth, seventh. All the elements of this group are highly electropositive in nature. So we are calling them metal. And there is also some other metals in the periodic table in D block also. You can also find them in B block. But S block metals are they are having some unique feature. The feature is they are very reactive. Okay, they are in the left hand side extreme. Remember what I have said. So they are very reactive. They are highly electropositive. Highly electropositive means they will try to lose electron very easily. Now, what is the reason behind it? When they are losing this outermost electron, they will achieve the noble gas configuration. So when sodium is losing electron, it will reach neon configuration. When cesium is achieving is losing electron, it will reach xenon configuration. So these are the reasons that why they are so much electropositive, why they are so reactive, because they achieve noble gas configuration. So if we are representing all the elements like capital M, because all of them are having metallic nature, so they will give this type of monovalent cation. Now you cannot expect that it will carry some 2+ charge. That is not possible at all, because if it is so, then you have to break this noble gas configuration, which is really energy requiring process. So that is why you will never find oxidation state 2+. Actually, not just 2+. Alkali metals, there is only one oxidation state, which is +1 oxidation state. You cannot expect any other oxidation state, and the reason is this. So alkali metals have only one oxidation state. So here we have seen the electronic configuration, also why they are so reactive. Because if you really want to understand why some element is reactive, basically you have to focus on their electronic configuration. That is how many electrons they will try to lose. And when you will try to understand their oxidation state, then also electronic configuration is required. Okay. Now we will discuss some atomic properties. So these atomic properties, remember in the periodic table chapter, there we have first idea of these atomic properties. Atomic properties means what I'm trying to say. Atomic radii, that is size actually. Then you can talk about ionization energy. Then we can talk about electronegativity. Then electron affinity. So these are the different atomic properties. So here we will discuss their size. Now when I'm saying size, you can have it in two forms. One form is the atomic form. So atomic form is it is neutral. There is no charge. It is simply Na, Rb, K. But when I'm saying ionic size, that is ionic radii, now what I'm trying to say, I'm basically focusing on M plus. So now it is not sodium, it is Na plus. It is not K, it is K plus. So from Na to Na plus, after losing one electron, now we are having this type of plus one charge, right? Now we will see here in this graph, you can see two lines are there. So this is for the black one is for the atomic radius, which is this is lithium, then sodium, then potassium, and the gray one that is for the ionic. Now ionic, it is starting somewhere in between 50 to 100. This is radius in picometer, and it is ending somewhere just below 200. Though in some books you can find these values little bit plus minus. That is here, suppose it seems lithium is 50, in between 50 and 100 exact. So you can find it a little different, but that doesn't matter. More or less, this is the trend. Important point is, as you are moving from lithium to sodium up to francium, whether it is atomic radii or ionic radii, in both cases there is increase, isn't it? Which is clear from this graph. There is smooth increase. There is no break or anything unexpected. Now, one thing that is true for all these elements is that when you consider the neutral element and when you consider its oxidation state plus one, obviously the size of M, it will always be high, because when you are removing some electrons, the size will always decrease. It is not just for alkali metals, it is true for any element. Suppose you have any element E. When you are adding electron, it is converted to E minus, the size will increase. And when you are removing electron, you are making some cation, obviously the size will decrease. It is true for any element. Okay, so here also it is the same thing. So being the first element of each period, what it means? It means, just think about potassium. Which period? It is fourth period. Now in the fourth period, it is the first member, isn't it? Similarly, if you consider second period, the first member is lithium. So all these elements, they are basically the first element of different periods, right? So being the first element of each period, alkali metals obviously will have largest atomic and ionic radii in their respective period. So now we are focusing in the period. In the periodic table chapter also we have seen it details that when we move from in periodic table, if you take any period and when we move from left hand side to right hand side horizontally, then there is a decrease. Though there is some discrepancy and exception, but except those factors, if you see in general, there is always decrease. So obviously in any particular element, as they are the first element, so they will have largest atomic radii or ionic radii in that respective period. So if it is lithium, then in the second period it will have higher size. If it is potassium, in the respective period, that is fourth period, it will have higher size. Now what about when you are moving down the group? There is a progressive addition of new energy shells. So principal quantum number is increasing. There is one new energy shell added. So obviously both atomic and ionic radii will increase, and that is the reason in this picture, in this graph, you can see whether you take M plus. So this line is for M plus and this line is for M. So whether you take M or M plus, in both cases down the group there is increase, and that is expected because of this addition of extra shell. And monovalent atoms are smaller than the respective parent atom, and that is expected. Size is high for M. Next atomic property is ionization enthalpy. So in short, it is IE. You can also say ionization energy. They are having the lowest ionization energy compared to other elements in that particular period. Because see, they are having the largest size. So removal of the last electron, which is ionization energy. Ionization energy means the energy that you have to provide to remove the most loosely held electrons, right? So here when we move electron in that particular period, it will be easier for the alkali metals, that is the first member. So in a particular period, suppose if you choose third period, sodium is the first element, so they will have lowest IE, that is ionization energy. Now, what about down the group? What is the trend? When you are moving down the group, two things you have to consider separately. The first point is, this is the first point, number of inner shells are increasing. That is true. Now, when it is increasing, it will also increase the magnitude of the screening effect. That means if you consider this is the nucleus and outermost electron is somewhere here. Now, when these inner shell numbers are increasing down the group, obviously the screening from the positive charge of nucleus, the screening effect for this electron, that is increasing. Now when it is increasing, that is the screening effect, then ionization energy, that should increase. Sorry, that should decrease. Okay, it is wrong, it is decrease. So number of inner shells are increasing, magnitude of screening effect. So it is as if hiding this hiding this electron from this positive charge. So this nucleus cannot attract this electron much. So you can easily remove the electron. That means ionization energy is not very high. But there is also another factor. When you are moving down the group, nuclear charge is increasing. Now what it means? Suppose you are moving from lithium to sodium. Here atomic number is 3. Here atomic number is 11. That means if you think about proton number, electron number are always same. So atomic number is proton number. So 3 protons. Here you have 11 protons. So obviously nuclear charge, that is a positive charge in the center, that is very high. So when it is high, the attraction for this outermost electron, that will also increase, and as a result ionization energy, that we have to provide more energy to remove this electron out. Now, so there is two opposing effect going on simultaneously. But who is winning? Which effect is outweighing? It is basically the first effect. So down the group, number of inner shells increasing. There is also increase in nuclear charge, but this effect is ultimately, it is not important. The ultimate effect, that is a combined effect, is down the group ionization energy increases, and that is because of this reason, that is number of inner shells are increasing. So the first effect is defeating the other effect. So the combined effect is down the group ionization energy decreases. So this is decrease. So here we have ionization energy in kilojoule per mole unit in the y-axis. So here for lithium, it is cutting somewhere 500 value. That means its value is 500 something in kilojoule per mole. Then when you are moving from lithium to sodium, there is decrease. Now one more important property is also there. It is true that it is decreasing from lithium to sodium. There is smooth decrease. But see, when you are moving from sodium to potassium, this difference is very high. But this difference, it is not so high. So this is also another important observation. Fine. So this is the first ionization energy values we are talking about. Now what about the second ionization energy? First ionization energy means the energy required to remove the first electron. That is, remember, noble gas configuration within third bracket, and then it is NS1. So basically you are removing this electron, and for that look at the values. 526, this is 526, then it is 504. So values are mentioned, that is smooth decrease. Now look at the second ionization energy. It is also decreasing down the, but look at the value, just compare. It is 500 something and it is 7,000. 500 something, 4,000. So it is 4 digit. So it is very high compared to the first one, and that is expected. Now I am not saying that you have to remember all this, but why you should have some qualitative idea. That is the range of second ionization energy, because related to these atomic properties questions are very common. So it is the range is 2000 up to 7000. This is the range. Now why this second ionization energy is very high? Because when you are removing the second electron, basically you have to break this noble gas, which is really difficult. So the second ionization enthalpies of alkali metals are very high, as removal of second electron destroy the stable electronic configuration of noble gas. Fine. So these are the ranges. For first ionization energy, it is 300 up to 500 in this region, but it is 2000 to 7000. This is the range. Next atomic property is hydration enthalpy. What is hydration enthalpy? Though we have discussed it several times, but still I will once more I'll say it. What is hydration enthalpy? Suppose you have any cation, I am saying M plus, or suppose you have any anion. Now when these ions, they are present in water medium, basically you can also say solvation enthalpy, but mostly we are interested more in water, so that is why we are talking, that is a solvent is water, so that is why the term is hydration enthalpy. So M plus, it is when it is free, it will be simply like this. Just take sodium plus, it is free sodium plus. But when it is in water, the water molecules, there will be some partial positive charge over hydrogen and partial negative charge over oxygen, 2 del negative charge. Now this negative charge, they will be attracted towards this M plus. So as a result, what will happen? Surrounding this M plus, it may be Rb plus, K plus, Na plus, whatever it is. But surrounding these cations, these water molecules, they will remain surrounding this. So as a result, what will happen? This positive charge as if it is somehow balanced by this oppositely charged O minus. Though it is partial, but still there will be some kind of stabilization. And when there is stabilization in the system, there will be some energy release. And when I am saying energy release, it must be with some negative sign. So look at the values. Enthalpy of hydration for lithium plus minus 550. So all are basically minus. So what it means? It means in all these cases, energy will be liberated, because the system is now becoming more stable when it is surrounded by water molecules as solvent molecules. Okay. Now, if you are thinking why ionic radius values are there, so we will also come to that point. Why ionic radius values are there? So there is reason for that. So these are hydration enthalpy that you are seeing here. You can consider Na plus. So free Na plus, suppose it is like this. But when it is in water, water molecules will be surrounding it. So for simplicity, only 3 water molecules drawn here, but it may be more than that. Fine. Now, how many water molecules will be surrounding? That depends on the charge density. Don't think it is dependent on size only. So cesium is a very large size, so many large number of water molecules will be surrounding it. No, that is not the explanation. The explanation is it depends on the charge density. Now charge density means what? Just simply think about normal density. Normal density means what? Mass per unit volume, right? Now when I'm talking about charge density, it is charge by volume. Now all are having same charge. The charge is +1. So charge is common. Now if you are dividing it by volume, so volume is increasing as you are moving down. So for lithium plus, the charge density, suppose I am writing here lithium plus, its charge density, if you compare with cesium plus charge density, obviously lithium plus will be having higher charge density compared to cesium plus. Why? Because in both cases, this denominator and numerator, if you think about, plus 1 is common, but volume is high for cesium plus because size is high, volume is also high. So volume high means overall this ratio will be very low. So maximum charge density is present in case of lithium plus, and when charge density is high, this type of water molecules surrounding it, that amount, that is the hydration amount, also increases, and that is the reason why this enthalpy of hydration values, if you look at the numerical values, forget about the negative value, look at the numerical value, it is maximum for lithium, and as you are moving down the group, it is decreasing. Why it is decreasing? The reason is this, because of this size increase, and size increase means volume increase also. So that is why here in this column, as you can see, size is increasing down the group, that means volume is also increasing. So as size is increasing, volume is increasing, charge density decreases. When charge density decreases, hydration amount decreases, and that is the reason in case of lithium plus maximum stabilization you can expect, but as you are moving down, stabilization is obviously there, but the amount is decreasing. So now what are the conclusions we can draw? The alkali metal ions are extensively hydrated in aqueous solution. So that is common for all. But if you consider the order, decreases with increase in size. So this is the order. Now when we are considering the order, we are just focusing on the numerical value. For lithium it is 515, for sodium it is 405. So just focus on numerical value. Don't think including negative sign, because then order will be different. So it is just based on the numerical value. We are saying down the group there is decrease. So lithium salts are more soluble. More soluble means it is more hydrated by water molecules than the salts of other metals of group 1, and because of strong solvation of small size lithium. So the same explanation is charge density is max. So water molecules surrounding it, that amount is also high, that means solvation is very high. So more stabilization, more amount of energy release, hydration energy is very high. When I'm saying high, don't consider the negative sign. I'm just saying high amount of energy will be released. So that is why there is minus 515. Fine. Next property. This is very unique property for alkali metals that you will not find for other elements. You can find it a little bit for is group 2 also. When we'll discuss group 2 alkaline earth metals, then also we'll see the same property, but it is mostly that is, you can say it is restricted to these two groups. You will not find this type of characteristic property in any other elements. So this is so unique for these two groups that just from this flame color test you can even predict. Suppose you have some unknown sample of sodium, you have some unknown sample of potassium. So from the flame color you can have some idea that whether these elements are present or not. Okay, that is inorganic salt. When we test, we can do this characteristic, we can check whether this characteristic property are present or not. So if this, it is showing some particular, there is particular color fixed for each metals, sodium, potassium. So which color you are seeing, depending on that you can predict which element is present. So when the alkali metal salts moistened with concentrated HCl are heated on a platinum wire in a flame, basically this is concentrated HCl, it is required because if in the platinum wire that you are using, if there is some impurity, suppose you have done some other test previously, so if still there is some impurity in presence of concentrated HCl, that is destroyed. So now it is clean platinum wire. So that is why concentrated HCl mentioned. So when we are taking some little amount of alkali metal salt, suppose you have taken sodium chloride or potassium chloride in the platinum ion, very little amount, then the heat in the flame there is some heat, it will excite the valence electrons to higher energy level, because valence electron, that is the most loosely held electron, its movement to higher energy level, that can occur very easily. Now when it will drop back to its actual energy level, now this coming to the original position, it may happen either in one go or in several steps, that may vary. Now there will be some energy release. So when it is moving to higher energy, there is some energy absorption. Now when it is coming back, this energy will be released, and this released energy is emitted in the form of light. Now this jump from high to low, obviously this energy difference, there is a specific amount of energy. Now again I am saying it may be in one go or in several steps, but whatever it is, suppose if it is several, then also there is some specific amount of energy, that is summation of all this movement. That is, suppose it is not in one go, it is in 3 steps. So there is some amount of energy for these 3 steps, that is mixed frequency or wavelength, or it may be in one go. But whatever it is, there is a specific amount of energy, and when you are talking about energy, there is some particular wavelength or there is some particular frequency. Now, depending on this wavelength and frequency, there is specific color. Now, when you can see color, that means what? It is obviously in visible region. Otherwise, how you are seeing the color? So, this energy, that is some of these jumps, it is not that all the jumps in one go or several steps, all will be in visible part, but some of these jumps will be in the visible part of the spectrum. So that is why we can see color. So this color that we are seeing, don't think that it is a specific color. It is basically mixture of, or better say combination of individual colors, because it may involve several wavelength or it may involve several frequency. So suppose in lithium you are seeing some red color, right? Now don't think that it belongs to a particular wavelength. That is, no single value of wavelength is responsible. It may be mixture of that. It is a combined effect. So for lithium, sodium, there is specific color, but you may observe one thing, that for potassium, rubidium, cesium, it seems as if all these 3 are same. Though there is some, you can easily recognize the first 2, but these 3, it seems as if these 3 are almost same. But it depends on in practice and experience also. If you have previous experience how it is, that is the violet that you are seeing for potassium, there is maybe some difference with rubidium, but that depends on experience and obviously the mode you practice. So here some, that is the colors that are actually there, that is mentioned. So red, that is fine, and see, for sodium it is mentioned not just yellow but persistent yellow. That means this yellow specific color. So this yellow, it is not just the color of the flame. This yellow, though from picture it is difficult to make you understand, but when you will actually do the test, you will see this bright yellow color, that is very specific. You can easily understand, and this is persistent. It will persist for some. So sodium you can easily recognize from this flame. And then for potassium, it is lilac, reddish violet, blue violet. So though all these colors are basically related to violet, but still there is some difference. But maybe from a picture you are not able to understand the difference, but actually there is difference, and that comes with experience, the more you practice. Fine. So after finishing all these atomic properties and flame property, next you will start the physical property. Now physical property means boiling point, density, melting point, what is the outer appearance, whether they are solid, liquid, like this. All these are physical properties. So obviously all of them are solid, and all of them are silvery white in color, though there is some little difference. But if you first see them, all these elements together, it is in one word you can see it is silvery white. They are so soft you can even cut them with knife. Now you cannot think these for iron or copper, right? They are hard metals, but here you can do so. So they are very soft. So their densities are actually very low compared to other metals, if you see, and that is the reason you can cut them. And they are very light. That is, their weight is not very high. Suppose the same piece, same size, if you take for iron or if you take for sodium, obviously it is very light. because it's low density compared to other metals. And the density of alkali metals increases down the group. Though there is some discrepancy, the actual values we will see in the next slide. Here we are just trying to understand the qualitative, how they are changing. Then the density, it is actually increasing down the group, but potassium and sodium, when you move from sodium to potassium, you expect potassium to have higher density because it is mentioned here increase down the group, but that is the discrepancy. So when you will actually see the values in the next slide, it will be clear. So the main points are they are very light, you can cut them with knife, they are so soft, and the reason is their densities are very low. It increases down the group, though there is one discrepancy. What is their appearance? They are silvery white. Now, as we are saying, they are metals. So obviously metallic bonding will be present. Now, what is metallic bonding? We know chemical bonding, we know ionic bonding, but there is a term metallic bonding also, which is mostly for metals. So what is metallic bonding? We'll see. But here it is written that low melting point, boiling point. So their melting point and boiling points are not very high compared to other elements, and that is they are solid. So if you compare with some other elements, those are also solid. Suppose if you compare MP and BP, melting point, boiling point, you will see it is low, and the reason is weak metallic bonding. Now, what is metallic bonding? If you want to understand metallic bonding, you have to imagine the metals, their inside structure like this. So it is not, don't think that sodium is there with its outermost electron, then another sodium with its outermost. No, it is not like that. How it remains? It doesn't remains like this. It remains like this. Suppose there is one Na plus. It has already lost its electron because the electron is so loosely held. Then there is its neighbor Na plus, another Na plus. Now there is one electron which belongs to it. There is another which belongs to it. It is not like this. So electrons, they are actually so freely moving, so you will not be able to understand the electrons that are present randomly, which electron it belongs to which sodium, that is difficult to mention. So as if the whole picture, how you can represent, as if there is sea of freely moving negatively charged electrons. So these are electrons. So they are as if moving in these positive metal ions. So these metal ions, they are fixed in their position and the electrons are moving. So suppose this electron, it is here, but it may belong to this sodium. It may happen. Here I am talking about sodium. It is applicable for any elements. So this is actually metallic bonding. There is no fixed electron, not fixed to any particular cation. Okay. Now this type of metallic bonding, it is very weak because only one valence electron is present for alkali metals. So lower is the number of electrons involved in bonding, lower will be the strength. So weak metallic bonding, and that is why boiling point, melting points are low. So metallic bonding, this term is used, sorry, it is basically in metallic bonding, there is collective sharing of sea of valence electrons between several positively charged metal ions. So it is written as collective sharing. So it is not that this electron, it is belonging to this sodium plus. No, it may not be so. It is collective. This type of bonding is responsible for several characteristic properties of metal. So as we see, some metals, there is shiny lustre. It is because of this metallic bonding, because electrons are so freely moving. There is malleability property, there is conductivity, and for heat and electricity. So why we are observing this type of property? It is because of this particular type of bonding, which is metallic bonding, where you have freely moving electrons. Okay. Now we will actually see the physical properties. So physical property, here we have atomic radius, metal, though this is actually metallic property, that is the first two. So atomic radius, you can remember in separate slide we have already covered it, and you can also call it metallic radius, that is when it is still neutral. So these are the values. Then all are in angstrom, sometimes it may be in picometer or nanometer, it doesn't matter. So all of them must be in one particular unit so that you can compare. Then we have melting point and boiling point. Look at the melting points. They are not very high, less than 100, except lithium. Then we have a boiling point. Range is 1000 to 600, like this. Then we have fast ionization enthalpy. So these values we have already seen, all are near in the range 300 to 500. Electronegativity, it is not required for us to discuss separately because they are metals. So their electronegativity will be least in the whole periodic table. Metals means electronegativity will be very, very low. Look at the density. Down the group it increases, but discrepancy is there. Sodium is having higher density compared to potassium. So these discrepancies are very important to remember because based on these questions you may get. So it is not smooth increase, there is discrepancy. Hydration enthalpy, remember these values also we have seen. And what about standard potential E0 value? So E0 value means when in chemical properties we will discuss their reducing property, then we will go into the details. So here just I am giving you initial idea. Standard potential E0 value, it is expressed like this. First the oxidized state is mentioned, then there is oblique sign, and then the neutral state is mentioned. So M plus, it is accepting electron, it is converted to M. So this equation if we consider, or the reverse way also you can write M plus and electron. So here it is basically losing electron, and if you consider the first equation, it is basically gaining electron. Now look at the values, all of them are negative. Now when there is negative value for, it is basically standard reduction potential, and mostly if nothing is mentioned specifically, you by default you can consider reduction potential, but sometimes it may be oxidation potential also. Now reduction potential means the tendency to reduce other species, that is reduction potential. Now when it is very negative, the more negative is the value, that means reduction potential that is very high. So here these, from these values you can understand as all of them are negative, so their reducing property is good for all of them, but you can say it is maximum for lithium because it is the most negative, right? So from standard potential, reduction potential, we can get the idea how much reducing property we can expect. So all of them are good reducing agent because all of them are having a negative value for reduction potential. Okay. Next, chemical properties. Though we'll not be able to finish, we can discuss one or two. So chemical properties, one common point we know that they are very reactive. Now the reason for their reactivity is that is they exhibit high chemical reactivity. The reason is low value of ionization energy, and also whether they are very large in size, you can easily remove the outermost electron, and that means they can easily form cations, they can easily feed electron to some other species. So that is why their reactivity is very high. This is the reason. The reactivity of alkali metals as you move down from lithium to cesium increases because remember size increases. If the reactivity is related to ionization energy and large size, so obviously down the group the reactivity will increase because size is decreasing as you are moving down, and also ionization energy is decreasing. So to remove the loosely held electron, you don't have to provide much energy. It can occur very easily, right? So this is the reason. And as they are very electropositive, the most electropositive you can say, so obviously they will be specific, they will show specific reactivity towards the most electronegative elements in the periodic table. And in the periodic table, remember in the periodic table in the right hand side there is group 16, 17. I'm not talking about 18, just excluding that 16, 17 if you consider the elements that are present, oxygen or halogen, that is F, Cl, Bri. So they are the most electronegative elements in the whole periodic table. So as they are very electropositive, they will have a special attraction for these highly electronegative elements such as oxygen and halogen. So it is not that they do not form compound with other elements, but specifically it will have a tendency to form compound with these non-metals. And whenever there is compound between a metal and a non-metal, the nature of this compound will be ionic. So ionic bond is one is completely accepting electron, another species is completely donating electron. So metal will completely donate electron, itself will be converted to M+, and the non-metal, it will accept electron. Now depending on its valency, if it is oxygen, it will be accepting 2 electron, if it is halogen, it will accept 1 electron. Depending on that, negative charge amount may vary, but there will be negative charge. So positive, negative, that is cation anion, so it is ionic bond when there is high electronegativity difference between the two species which is forming bond. So as they are belonging to the two extreme of periodic table, the metal belongs to the left hand side and the non-metal they belong to the right hand side, right? So maximum electronegativity in the right hand side and lowest electronegativity that is in the left hand side. So when they are forming compound, obviously the nature of this compound it will be ionic compound. Okay, so the first reaction that will be reaction with air. Now when I am talking about air is there is presence of oxygen and nitrogen. So reaction with air, it means basically how the metals are reacting with oxygen and how they are reacting with nitrogen. Okay, so all the alkali metals when they are exposed to air, which is basically you can say exposed to oxygen, there is rapid tarnish. That is, if you look at their surface, basically they are so reactive you cannot keep them in open air. You have to keep them under special condition. Mostly they are kept in kerosene oil or any other oil, so that it is not in contact with air. And as you are moving down, as their reactivity is increasing, so this explosive nature, when you are bringing it out of this oil, that will also very increase. So you have to take care of this fact more as you are moving down. So lithium even you can handle when it is you are bringing it out of the oil, but handling sodium and even potassium, it is very dangerous. Okay, so when it is in exposure to air, the first thing that will happen, there will be rapid tarnish on their surface. So the shiny surface, now it will no longer be shine. The shine will go. So there is some rapid reaction with oxygen. And for lithium and sodium, okay, fine, you can bring them out of the oil and you can cut them with knife. But if you are trying to do it with potassium, there will be explosion, and as you are moving further down, cesium or rubidium, it is really dangerous. Okay, so there is rapid, they tarnish rapidly because some oxide is formed. That is a reaction between the metal and oxygen already happened. That is why there is oxide formation. So the shiny nature is gone. Okay, so we will have to end here. We are at the end of the session. We'll finish it in the next class. Thank you for listening.